welcome you all for the lecture on mathematical analysis of recursive algorithms. So last class we discussed about last two lectures we discussed about a mathematical analysis of non-recursive algorithm with examples. 2 examples each section. So today we are going to discuss steps for analyzing recursive algorithm and few examples. Okay, so step 1 is about first, in previous non-recursive algorithm the step 1 is in input size. Okay, so here also you want to indicate the input size, decide on a parameter indicating input size. So first you see the size of input given, input size. Second one is basic operation. Okay, identifying the algorithm basic operation. Third one, so these two steps are same. Okay, the next step is also the same. How many number of check the number of times the basic operation is executed. Check the number of times the basic operation is executed. Okay, so here a basic operation is executed can vary on different input size of the same size. If it can be worst case, best case and average case analysis, it can be investigated separately. Okay, then fourth step is set up the recurrence relation. Okay, here fourth one, the first 3 steps are same for recursive and non-recursive algorithm. The fourth and fifth step will be differ. Fourth one is set up a recurrence relation with an appropriate initial condition. So while setting the recurrence relation, you must ensure initial condition, comma, for the number of times the basic operation executed. Okay, then fifth step, the last step is solve the recurrence relation. Solve the recurrence relation. So these are the 5 steps used to analyze the recursive algorithm. So for this we are going to discuss an example. So example 1. So here the example 1 is nothing but a factorial of given number. Okay, So here I'm going to describe the problem. Compute the factorial function f of n equal to n factorial for an arbitrary non-negative integer n. Okay, so this is the problem definition. Here how you define n factorial equal to 1, 2 up to n minus 1 and n. Okay, so this is the definition for n greater than or equal to 1. Okay, why mention it as n greater than or equal to 1? 0 factorial is equal to 1 by definition. So we can compute f of n equal to f of n minus 1 into n with the following recursive algorithm. So here I am going to write an algorithm with algorithm heading and then name of a factorial. For example, f of n. F is the function name, n is the argument passed here. Then problem description given in command lines. Compute n factorial recursively, because we can solve it non-recursive manner also. So that mention it is a recursive manner. Input is a non-negative integer n. Okay, output. This is the way of writing an algorithm. First algorithm, then function name, parameter list, description, input and then output. Okay, output is the value of n factorial. Okay, next, first step, without declaration, just you can write a basic, that is an important thing only. If n is equal to 0. If n is equal to 0, no need of proceeding further. Just return 1 because 0 factorial is 1. So return 1. Okay, else. Otherwise, there is a recursive call return f of n minus 1 star n. This is the recursive call. Okay. I will once again explain the recursive with a trace out of a value. If suppose, okay, if suppose n value is equal to, okay, if suppose n is equal to, first if n I am taken n is equal to 3. N is equal to 3 means first iteration check if n is equal to 0, condition fail. Next, it will work else part. Return statement, you have a recursive call f of what is n? 3 minus 1 2 star what is current n value 3. This is the first execution. In the second, after that, if f of 2, again it will call f of 2. Here n value is 2. Again check n is equal to 0, condition false. Then else f of 2 minus 1 star, already you have a 3, now 2 star already 3. Okay, 3 star 2 star, again the f of 1. Then f of third time f of 1. F of 1 means again check n is equal to 0, no, not because n value is 1. Else f of n minus 1, n minus 1, 1 minus 1 0, okay, 0. Here already you have a value, that is f of 0, f of 0 star, 1 star, 2 star, 3. Again it will call the same fourth time, f of 0. Here check n is equal to 0, true, return 1. Where it returns 1, it will return 1 here. Okay, so 1 star, 2 star, 3 star, star 1. Totally 2 star 3 star 1, 6. So 3 factorial is equal to 6. Okay, this is the working principle of factorial. Now we are going to analyze this algorithm, factorial function, the step 1. Okay, step 1 in mathematical analysis of recursive algorithm. Here also, what is the input size? The input size n, because we are passing the n value here, n may be varied. Then step 2. Step 2, you want to identify a basic operation. So what is a basic operation here? The basic operation is computing factorial, that is multiplication. Okay, so basic operation, so computing factorial f of n minus 1 star n. So here the operation is multiplication. Okay, basic operation is multiplication. Step 3. The recurrence function call can be formulated as, okay, how many times the basic operation get executed, that is the third step. Okay, so I can write this, the recursive function, because it's not an iterative one, it is a recursive function call can be formulated f of n equal to f of n minus 1 star n for n greater than 0. Then the basic operation comma multiplication is given as m of n, multiplication, so that I am write it as m of n, and m of n is the multiplication count to compute factorial of. So how many times the factorial function is called, that is number of times the factorial function get executed. Step 4. In the step 3 itself we can going to formulate it like, what is m of n, number of, m of is the multiplication count, is equal to m of n minus 1. This is the multiplication count, number of time it will be called, plus 1 time to multiply f of n minus 1 by n. Okay, this is for to compute f of n minus 1. Okay, this is for to multiply f of n minus 1 by n. So lastly we can call this f of n minus 0 one time, that one time you can multiply this n with this f of n minus 1. Okay, that is f of m of n minus 1 plus 1. Okay, step 4. So in this step the recurrence relation is obtained, that here you can solve set up the recurrence relation, right? Okay, so the recurrence relation is obtained in step 3, that is m of n equal to m of n minus 1 plus 1. Okay. Next, step 5, solve recurrence relation. We already formed recurrence relation in the previous step. Solve recurrence relation. This is new word to you, recurrence relation. The recurrence relation is only used in this recursive algorithms. So for solve the recurrence relation, we have two methods. One is a forward substitution. Second one is a backward substitution. So both are very, very important. You want to solve in both the methods to prove your correctness. Okay. So first I am going to apply a forward substitution. Forward substitution. See, so what is meant by forward substitution? If I am asking tell the numbers from 1 to 10 means how you tell in a forward manner 1 2 3 4 5. Then if I am tell the numbers from 10 to 1 means you tell it as a 10 9 8 likewise. So 1 2 3 is a forward manner, 10 9 8 7 these are the backward manner. Okay, likewise the forward substitution is, here you have already formed a recurrence relation m of n is equal to m of n minus 1 plus 1 for n greater than 0. So here from this formula you are going to apply a forward substitution. So you can take the n value from 1. Why we taking n value from 1? Because n greater than 0. So we can't take the value 0 here. So first n is equal to 1. You substitute n is equal to 1 in this equation. M of 1 equal to m of 1 minus 1 plus 1 is equal to, here is equal to m of 0 plus 1. So what is, you want to replace m of 0 with some value, no? So here see, m of 0 is equal to 0. Why I am writing like this? And can you judge? Because n value here, n is equal to 0 means no multiplications. There is no basic operation will be executed, right? So m of 0 means n value is 0. There is no basic operation going to performed. Okay, there is no multiplication is performed. See, in this algorithm we written n is equal to 0, it will not execute the basic operation, right? Now see this algorithm once again. See this algorithm. If n value is equal to 0, it will not move to the basic operation, because the basic operation is multiplication. So multiplication will not work if n is equal to 0. It will directly execute this statement and come out. So it will not proceed to the else part. So that if n is equal to 0, there is no multiplication. So n is equal to 0. M of 0 is equal to 0. Okay. Because no multiplication. And next, second, you can solve for one or two numbers. It's enough. M of 2 minus 1 plus 1. Okay, m of 2 minus 1 m of 1 plus 1. So what is m of 1 in a previous step? That is m of 1 is equal to 1. Okay, answer is 1. 1 plus 1, 2. So m of 2 equal to 2. Then m of 3. N is equal to 3 means here n is equal to 2. N is equal to 3. M of 3 minus 1 plus 1. M of 2 plus 1. What is the m of 2 in previous step? 2. 2 plus 1, 3. So m of 3 equal to 3. M of 2 equal to 2, m of 1 equal to 1. These are the forward substitution method. Okay, why you going to solve these two methods means you want to prove the correctness of an algorithm, you want to prove using some mathematical induction, right? So that we are solving like this. So second one is a second method is a backward substitution. So your kind attention, please listen very seriously, it's important thing. Backward substitution. So backward substitution, again you take and write the mathematical induction. Okay, m of n, it's a recurrence relation, m of n minus 1 plus 1. Okay, this is the recurrence relation. So here the m of n can be written as what is the value before n? See here, for example, I'm right 1, if you write 1, 2, 3, 4, here up to last value is n. What is the before value of n? N minus 1. So before n minus 1, n minus 2. Right? So for n minus 1, the term you write it as, what is the previous term for n? M of n minus 1 plus n. So m of n can be written like this. Okay, now I am going to substitute in a backward manner for this term. For m of n minus 1, what is the previous term for m of n minus 1? M of n minus 2, right? So I want to elaborate this term m of n minus 2 plus 1. So the whole term will be written like this, then this plus 1. This is the first backward substitution. Okay. Next, I am going to simplify n minus 2 plus 1, this plus 1 and this plus 1. Okay. Now I am going to elaborate this term. What is the previous term for this n minus 2? N minus 3, right? Is equal to m of n minus 3 plus 1. So the whole term for this one, then again you have already 2 plus 1 and plus 1s here. Okay. So how can I write this? M of n minus 3 plus 1, 2, 3. Okay. This is m of n. So from backward substitution, I get the values like this. M of n is equal to m of n minus 3 plus 3 until. Okay. So now I am going to simplify this value m of n equal to m of n minus I plus I. Okay, instead of this constant value, I am replaced with here same values are here. So I am replaced with the same variable I. So to prove correctness, the correctness, prove m of n equal to n by using mathematical induction. See, in previous lecture we discussed about the fundamentals of algorithm problem solving, right? In fundamentals of algorithm problem solving, there is a fourth step called prove correctness. Fifth step is called a proving correctness. So proving correctness, we are using some mathematical induction. Okay, so for that only we are doing these calculations. So for that prove an induction, you have a first basis. So basis is let n equal to 0. So if n value 0 for factorial, n value 0, what it happens? M of n equal to 0. So m of, instead of n, m of 0 is equal to 0. We already know that. Okay. Now you want to prove by induction. This is the basis. Using this basis you can prove by induction. So first, so everything is assumption here. If we assume m of n minus 1 equal to n minus 1. So why we taken like this means you have a question, right? Why we taken like this? This is means this is we taken for just proving the our algorithm is correct. Okay, then m of n equal to, so instead of m of n I am going to substitute the value m of n minus 1. So in the m of n minus 1 plus 1, here I am replace this with this one equal to n minus 1 plus 1. So what happens? M of n is equal to n. Okay, this is one method. Or I can using one more thing, that is m of n equal to, in previous step we got this one m of n minus I plus I. Okay, so here if I is equal to n, I value is equal to n means instead of I we can take as n, m of n equal to m of n minus I n minus n plus I, instead of I am replaced with n. So m of 0, n minus n 0 plus n. So m of 0 is 0, right? 0 plus n, then m of n equal to n. So it can be proved for n minus 1 and also n. Okay, so it will be equal. So our calculation is right for a given algorithm. So the time complexity, okay, so the time complexity t is order of the n, is the time complexity of factorial of given n number. Okay, so do you have any doubt? Please work it on. Okay, because without practice you can't write this in your exams. Okay, thank you for listening. We will meet you on next session.